So at this point, we're just going to continue from the previous demo. We interpolated the bathymetry of, say, the eTopo5 satellite product to a variable h, which is on the model grid. And once again, we can plot this by using the PLCM command, GRD. And so this is the bathymetry. So the next thing that we're going to do is we are going to store the bathymetry file. Okay, so I did this. And we're going to store the topography onto the grid file by executing this command. So this is store raw topography here. And now we're going to reload our grid file, ROMs. Okay. So once we did that, we can now plot the grid file topography, grd.h, onto grd, which is our grid. And this is what it looks like. Now you can see that when I stored the topography, I basically set to 0 all the values that are on land, and I set to positive depth all the values that are in ocean. So now the depth, the positive value, means it's deep in the ocean. Okay, so that's that. So let's go back to this script. Then the next thing is to smooth the topography. Okay, and to add additional other parameters. Why do we want to smooth the topography? Well, the problem is that if you look at the topography usually has a very steep gradients that could actually cause computational instabilities or actually computational error in the model. In particular, in ROMs, there's a well-known issue associated with the computation of the pressure gradient terms of the equations, and computing the pressure gradient term on these coordinate systems that are, as we will see later, following the topography, will actually encounter some errors if the slope of these coordinate system is very high in regions where the topography has a very high steep slope. So how do we know how to smooth the topography? Well, first of all, before we do that, let's define a couple of parameters. In particular, let's decide that we will have a minimum depth of, say, 20 meters. Given that this is a 15-kilometer resolution, we don't want to have a minimum depth, say, of a meter, because it doesn't make much sense. We're also going to set a maximum depth because we likely don't have data to constrain the model solution below 4,500 meters. And then we're going to, so let's do these two things. Then in this third statement, we're going to load in this local variable hraw the raw topography that we just extracted and saved in the grid file, so in this GRD. And we're going to just set that the raw topography minimum value has to be hmin and the maximum value has to be hmax. So I'm just going to do this, okay, here in my MATLAB. I'm going to close all the figures. And then I'm going to plot here with the PLCM command the hraw array, but I'm going to compute the R value of this hraw array. So what's the R value? The R value is really just the slope of the topography. And so if you plot that, it goes from 0 to 1, where 1 is highest and 0 is no slope. And you can see that in proximity of the continental shelf, around here, the slope is very steep. It's about almost equal to 1. This is the relative slope. So it's basically, if you do a type R value, which basically lists the routine, you'll see that this R value function, all it's doing, it's really taking the differences, the delta, the derivatives in the x direction, the derivative in the y direction, and it's normalizing it by the depth. Okay. So that's really what it is. So anyway, so if you do that, we set in MATLAB, and we look at the figure here, you find that it's very steep. Now, practically, by experience, we like to smooth the topography so that the R value is below, say, 0.35. This is a kind of a magical number that I'm not sure where it comes from, but and so I cannot tell you. But if you do that, typically the errors that come from the pressure gradient computation are perhaps small enough that that you can that your calculations don't look like crap, basically, said in very simple terms. Okay, very well. So at this point, then we have to start the smoothing. And here you have various options, okay? In fact, you have three options. Option one uses a Shapiro filter. Now, the Shapiro filter, let's execute it and then show you what type of smoothing does. Okay, so we're just going to do this Shapiro filter smoothing. And now this is the R value, after the smoothing, and you can see that in fact is below about 0.35 and everything is smoother. Now we can plot, in fact, the topography associated with the new topography, which is in this temporary array. And so you can see this is now our smooth topography, which is very different if you compare it to the raw topography that we began with. You can see that it smoothed out all that kind of features. Now if we look at a transect around here, for example, let's plot one transect here. Let's plot, say, TMP of all the, say, let's transect along number J30. Okay, in fact, let's put a minus because we want it. Okay, so here we have that this is you can see here the continental slope. Okay, and then it goes down and so forth. Now on top of this, you can plot the original slope of the topography, which was H raw, and let's plot this in color red. And so you can see how in proximity of the slope here, you have really smoothed out the red curve, which is the original slope, into something that is smoother in transition towards the coast. And you also have removed all these spiky features, so that when you have the vertical coordinate system, which follows the topography here, it will actually follow topography in kind of in a smooth way here, and not in like doing things like this, which would lead to significant error in the pressure gradient term. So this is one option of the Shapiro filter. Another option that you have is one that Perrick-Benven wrote, and it basically uses this smooth grid. And what it does is really, instead of smoothing stuff in physical space, it actually smooths things in logarithmic space. So it will preferentially smooth out features that are really more steep, and not smooth things that are not and not very steep. So it will selectively smooth more things that are very, very steep. So in this, if you want to use this approach, you define the R factor, which is the R value, the maximum R value that you want to have, or maximum slope of topography. In this case, let's say 0.35. And then we just, oops, sorry, ask undo. And we're just going to execute this here. Okay, so it smoothed that, and we can go now again in the figure, and we can plot a profile of the new smooth version, which is again contained in this temporary array. And in this case, we're just going to plot it as a green curve. And so what you see here is that if you look at the continental slope, there's a difference between the blue curve, which is the Shapiro filter, and the green curve, which is this logarithmic smoother of Perrick-Benven. And what you see, if you look at the red curve, which is the original topography, you see that the logarithmic smoother, kind of kept, the right sill depth here, the depth of this thing, and then it kind of, smoothed out from here onward to smooth this very steep slope. Whether in the case of the Shapiro, the Shapiro filter did not maintain this kind of shelf here, but it just, went straight down and it smoothed this red line. So you can see that these are two different types of smoothing. Here, the logarithmic one kind of smooths, outward from the shelf and so forth. And this is the main difference, in the shelf region. If you go away from the shelf, you could see that the green and blue are not very different, and the green maintained a little bit more, these features, so that the R factor is below 0.5, and so it didn't really smooth them out so badly like the Shapiro did. So if you're a beginner, I think the logarithmic smoother is a very good option that you can use, and I would encourage you to use that, which is so that's that. And you can plot now also the topography that you did with the logarithmic smoother, and you can see that this one looks a little bit more has more features than the one that we smoothed with Shapiro, and maybe to some extent it's also closer to the raw topography. which I'm going to plot now in a different window. So this is the raw topography. So if you compare this raw topography to this one, the one smooth with the logarithmic, you see that it is smoother, but it did retain some of the characteristic features here, and so it's less smooth than the Shapiro one, and yet you've reduced the R factor within within the range that you need to minimize these pressure gradient errors. Okay, so that's one example of smoothing. You also have a third option, and this is a routine that Hernan Arango wrote. And this is basically a Shapiro filter again, but in this case it only applies the Shapiro filter in regions where the R factor is too high. So if you want, you can try this routine. I'm going to stick with the logarithmic one, so I'm just going to do it. Okay. And so again, this is the R factor that results from using the logarithmic filter. I'm happy with this. I close this. And now the next step here is to save this temporary array into the grid file in the variable h, which maintains the topography. So I do that. And at this point, I am kind of done with the smoothing, end of smoothing, and I can plot a figure that kind of summarizes all I have done. So I'm just going to do that. Okay, it's taking some time. Okay. So, oops, oh, I closed it. That's not very good, so I'm going to have to redo it. Okay, so I'm going to maximize this figure. And so this figure shows me the raw topography that I started with, the one that I extracted from eTopo 5. This is the topography after the logarithmic smoother with the minimum depth of 20 meters, which is what I wanted. And you can see that also the maximum depth is 4,500, which we had set. And so you can compare these two. And if you want to look at the difference between these two, this is given by this map here, h minus h raw, and it shows how, in fact, after you smooth, the maximum differences are in the proximity of the continental slope, where you have, selectively, made the continental slope shallower or deeper, on one side or the other. And so you could see that in these regions, the mismatch between the true topography and the smooth topography could be of the range of 2,000 meters, which there's nothing you can do about. But hopefully typically it will not destroy your solution so badly if you are working at this scale, coarse scales like the one that we selected, which is about 15 kilometers. And then here it also represents you the R value associated with the smooth version of the topography to make sure again that these R values are within the range acceptable for this pressure gradient error. Okay, and so with this now we are complete with the smoothing process. And the next point is to do the masking, the land masking, in the next demo.